With that, it's really a very unique privilege and great pleasure to introduce Mike Aziz, the Gene and Tracy Sykes Professor of Materials and Energy Technologies from Harvard University, as our Andlinger Center Highlight Seminar speaker today. Mike got his PhD from Harvard. Then he spent a couple years at Oak Ridge National Labs as a Eugene Wigner postdoc fellow, where he was studying ion beams and laser beam modification of materials. But then he returned to Harvard, and he was there as an assistant professor, full professor. He was the Gordon McKay Professor of Materials Science before his current chair position. So for those of you who don't know Mike, Mike's a long-standing and well-respected leader in the field of materials science. His work over the years has spanned many different areas, ranging from fundamental materials science of semiconductor processing, all the way up to entrepreneurship in the area of carbon capture and sustainability. And among his most recent research interests, and we're going to hear about today, are novel materials and processes for energy technologies and greenhouse gas mitigation. Of course, over the years, he's won many, many awards. I can't list them all here, and he is a fellow of a number of organizations, such as the American Physical Society and Materials Research Society. Now, I'm going to go on a little bit longer because I said it was a unique privilege, because those of you who don't know, Mike was my PhD advisor. So now I'm not going to embarrass you. Just the fact that I'm here might be embarrassing, but I'll try not. And if you're looking for somebody to blame for who unleashed me onto this world, there's your guy right there. But, you know, really, in addition to being a world-leading researcher, he's also really an unbelievably dedicated educator, not just in the classroom, where he's coordinating a university-wide effort on energy and the environment, introducing new courses, writing textbooks, but also as a PhD advisor. And I can't say how lucky I am that he accepted me into his group all those years ago. And I didn't know anything about material science at the time. Our first interaction was me saying, "What's that diagram up there?" He's like, "You sure you want to be in this class?" But it really set the tone for what would follow. You know, he really taught me the importance of fundamental science and how that fundamental science can play a very central role in engineering and developments of technology. And really, most importantly, he taught me that it's really good to get excited about what you do and share that enthusiasm with those around you. And today we're going to be hearing about some of the enthusiastic and exciting work that he's doing on organic aqueous flow batteries. He's the inventor of a very new and promising technology in this area. He has a big program in this, and we're looking forward to hearing all about that. So without further ado, let's give Mike a welcome here, and we'll hear what he has to say.
Thank you, Craig, for that very kind introduction. I should add to that introduction, Craig Arnold was one of the most fun students I ever had to work with in the lab, and he's one of the people whose subsequent work I'm most proud of. So it's a pleasure to be back here. It's been a while. Last time I was here, I was doing nothing in energy and came here to learn, actually. And now this is what I consider possibly a really significant development, and I'm excited to tell you about it. So it's collaborative work with chemists. Roy Gordon, experimental chemist, Alana Aspuruguzic, theoretical chemist. I'll tell you their roles as we go. And I'm going to start, though, with just what it takes to store energy for the grid, because there's a lot more thought and effort that's gone into storing energy for vehicles than for storing energy for the grid, and the requirements are quite different. Who here has heard of a flow battery? Who knows what a flow battery is? Oh, about half. Okay, that makes my job a lot easier. I'll maybe go a little quicker through that. And I'm going to introduce some organic molecules called quinones, which I didn't know what they were 3 years ago, but now I've learned a lot, let's say, working with chemists. And we've made flow cells out of quinones that look really good. And I'll end by telling you a bit about where I think this is going to be able to take us. I don't know if this made news this far down in the Northeast, but a year ago, right, we had headlines saying wind is now competitive with everything but natural gas. Where's gas? There, 6.7 cents a kilowatt hour, and wind was less than 8, okay, and wind was beating hydro, coal, everything else. Nothing beats gas right now, but Last winter, the price of natural gas was 4 times what it is right now in Massachusetts. And 10 years from now, who knows where the price of natural gas is going to be. So if you are thinking about 10 years out or so, this is very big news. But gas, of course, is the wild card. It can kill everything if you power everything with gas. But we do have the greenhouse gas problem that we all know about now. Economically, Germany has gone very far in transforming their energy sources to wind and solar. And as a result, they now have days where there is too much wind and not enough consumption on the grid, and it actually has driven the price of electricity negative. Negative market prices for electricity are not good for stable markets. Right? And you can see the economists thought that this was bad as well, and they're worried now, very worried about storage. Turns out negative prices happen in the Midwest of the US pretty often. The purple here and the deepest blue next to the purple are negative electricity prices. These are real-time prices. Right? And so we see too much supply over here and a lot of demand over here. These are in dollars a megawatt hour. So divide by 10 to get cents a kilowatt hour. So that's 80 cents a kilowatt hour here, right? And negative 1 cent a kilowatt hour there, and even more negative there.
For practical purposes, you're not paying anything?
You can set up a device to consume electricity and be paid. If you can if you can afford the capital cost of that, then you should do that. The problem is that there's renewable energy incentives so that wind producers get something like 2.9 cents a kilowatt hour no matter what price they sell it for. So they'll pay you 2.8 cents a kilowatt hour to take it because they get 2.9 cents a kilowatt hour from the federal government as a renewable energy credit. Right. Now that may... The production tax credit is different in ways that I don't understand well enough to talk about when I'm being recorded for posterity. But, okay, transmission from here to here would be good, right? Except a few hours later it looks like that, and a few hours later it looks like that, so transmission isn't going to solve this problem. Storage could, right, if you could do storage cheaply enough. Now, California's decided to mandate storage. California has this problem that it's all in the same time zone and everyone has these solar panels, so the middle of the afternoon there's this bright sunshine and all this distributed electricity that's generated and being fed to the grid from everyone's rooftops, and then the sun sets on everyone at once as they go home and turn on the air conditioning. So you go from huge supply to huge demand, and that's really destabilizing. So California's mandating storage, which is really exciting for storage. The mission of people working in bulk storage is to make it so you don't have to mandate it, but you've got to start somewhere. So California's getting started. Okay. A fifth of the population of the Earth lives without access to electricity grid. So if you're one of those 1.4 billion people and you have electricity, and if you're fortunate enough to have electricity at night, it's because you have solar panels during the day and lead-acid batteries backing these things up at night. And of course, lead-acid is expensive, it doesn't last, and you've got the lead problem as well. So there's another possible place where inexpensive storage could make a big difference. Back to the grid, though. What the grid wants is this green curve here. All right, you see a daily peak in demand, 5 weekdays, weekends a little less. You see troughs that are, far above zero at night, though. And what nature gives you looks like this 3-week wind supply up here, or this 3-week solar supply here, right? Sunny days, cloudy days, always dark nights. And you can have several days end on end with no wind at all. And so the challenge of storage is to map something like this or this onto something like that. And my first student to work in this area, Jason Rugolo, asked the question, what does it take, just technically, in order to do this kind of storage? You might want to deliver completely levelized power. That's a simple thing to think about, anyway. And so I'll show you results for that. You also might want to take the grid demand and subtract base load and say we're going to provide base load by nuclear or something like that, and then just this up and down every day with storage. Or you might think from a small business point of view, I'm going to be a storage company, I'm going to buy electricity during the night, and I'm going to sell it during that 5-hour peak every afternoon where demand is the highest, and I'll make my profit that way. So the question is, what does it take in a storage device to do that? So taking what nature gives you and turning it into this, which we call grid minus base load, or constant output, or a square wave centered on the peak demand. If you run an electrochemical device to store energy and give it off in this manner, or just about any other storage device, you have a range of instantaneous efficiencies that depend on how hard you're driving it. So if you charge rapidly, you have higher overvoltages and higher voltage losses. If you discharge rapidly, the same thing. So there's no single efficiency in a device, but at the system level, on average, there's a system efficiency. And if you're storing electricity, that has to be really high because you have to pay for the electricity. And you have to give it back, and usually there isn't that much of a margin. So high efficiency is what people think is a really important thing here at the system level. And we have to turn a distribution of instantaneous efficiencies, which we can figure out how that's going to behave, into a high system efficiency, which basically you would spec. All right? And when you spec it, you have to spec two things. The two most important figures of merit that come out of a storage device are the amount of energy it can store, and that's in kilowatt hours, which is what you pay for on your electric bill, or megawatt hours if you're a supplier, right? And the rate at which it can deliver that energy out of storage, and that's kilowatts or megawatts of power. Right? And so the question is, all right, say you have a 1 megawatt nameplate solar farm. Right? How many megawatts peak power capacity do I need in my battery? How many megawatt hours energy storage do I need in my battery in order to turn this into this or this or this? And the ratio, what is that? The energy to power ratio is the number of hours you can discharge your battery at full power before it's drained. Right? And that's very different for different applications, and it's very large for these applications, as we will see. And the same question for wind. How many megawatts, how many megawatt hours, what's the ratio? Okay. So here's a prototypical electrochemical storage device, and let me take you through this. We've got voltage of the device in red, and here's a realistic curve. This is a system we were studying at the time. Here's zero current density, so that's the open circuit voltage. This cell was at about 1.4 volts of open circuit voltage. And if you charge it, you have to provide more volts than that. And the instantaneous efficiency, depending on the current density, is just the actual voltage you have to put in divided by the equilibrium voltage to put it in. And when you discharge it, you come down this curve. As the current density goes up and up, you get lower and lower voltage out of the cell. Think of just internal resistance. Nonlinear internal resistance is doing that. And the discharge instantaneous efficiency in discharge is the actual voltage divided by the equilibrium voltage. So there's a curve that looks like that, and that's one cell we were looking at the time. In order to get results that could be reasonably generalized, we used the linear potential approximation, which is this curve here. Turns out cells we're working with now are much closer to linear than this one, so it's an even better approximation. The voltage times the current density is the power density, voltage times current density, and that is the blue curve. So there's the realistic power density, and the linearized voltage curve gives us that dashed line, and that's just a parabola, of course, for power density there. And there's a peak galvanic current density we call pi, and if it's linear, then you just get closed form, simple algebraic expression for that peak power density, and that's an important figure of merit for your electrochemical storage device. It turns out, given the peak power density, you can get the instantaneous efficiency versus power density. Here it is. So here's efficiency, all right? And this is power density. So this is galvanic, and this is electrolytic, and it doesn't go above 1. And depending on the peak power density, if we go from 500 to 1,000 to 1,500 milliwatts per square centimeter, say at a given power density, the efficiency goes up and up and up. So we want more efficiency, we want more peak power density, right, or more area. But both of those things can cost you. And so the question is, how much peak power do you need to buy in order to get the efficiency up so high enough that you meet your overall spec round-trip efficiency for the system? And here's some examples of what a storage device would do, storing these wind or solar profiles. So for example, you've got a megawatt nameplate wind. All right, the wind has this wind profile has a capacity factor of about 1/3, which means on average you're getting 325 kilowatts. If you spec a round-trip efficiency of 85%, that means you're going to be getting on average only 276 kilowatts delivered to the grid. So here, these are the windy periods where the cell is charging. These are the calm periods where it's discharging, right? And you've got to store enough energy to give you levelized output during this 3-day period, and that's going to set the energy. And it turns out what you need in this case is about 0.5 megawatt of power, peak power density, and 50 megawatt hours of storage. Actually, that's off by a factor of 2, 25 megawatt hours, and here the ratio is about 50 hours. For solar, again, sunny days you're charging, and during the nights you're discharging. And with a round-trip efficiency of this number, you can work out what you need for power density. Here it is. And what you need for stored energy. Here it is. And the energy to power ratio. So this is telling you need to store energy for tens of hours to get you through a night, basically, or a couple of days to get you through a non-windy period if you're going to levelize wind and solar. And so you can just ask, all right, for a given specified system efficiency, how much peak power do I need? And those are the results I just showed you, those X's. And how much energy power ratio do I have? And those are the X's. Then you can vary the spec efficiency. Say I want 95%. Well, you see really diminishing returns here, is now I've got to get something like twice or more than twice the peak power, and that's going to more than double my capital cost, right? So there's some place where you're going to say enough, and this is 80, 90% of where people tend to say this is good enough. So here's all those delivery scenarios on one plot: constant output, grid minus baseload, square wave. So the square wave is in pink, and let's look at wind, for example, and let's look at grid minus baseload. For 95% round-trip efficiency, grid minus baseload, you need, for a 1 megawatt nameplate wind farm, you need about 2 megawatts peak power, and you need about 60 megawatt hours. That's what that says. And all of these scenarios give you, about 60 megawatt hours for any reasonable value of the efficiency of that wind profile, and about 16 for any reasonable value of the efficiency of that solar profile. And so those are round numbers about what it takes. Now, what do you get out of a lead-acid battery or a lithium-ion battery? Those are the curves for typical solid-electrode batteries. These things have only about 1% of the required energy for a given power to do this storage. To show you that in another way, let's look at, say, a 1 megawatt wind turbine, which would cost you probably about $2 million. Right? And you need to store about 60 megawatt hours in that. And you can buy a battery bank of lead-acid batteries that will give you 1 megawatt of power. How long does it last? Well, if you had my experience of not being able to start your car on a cold winter day and cranking and cranking and cranking the starter until the battery was drained, you know the answer. Right? It's about 12 minutes. Okay, so you don't even get a megawatt hour, you get a fifth of a megawatt hour. Okay, so you can buy 5 of them, now you've got a megawatt hour. But you want more, right? You need 60 megawatt hours. And so there you go. And now your $40,000 battery bank, which was only 2% of the capital cost of your wind turbine, has become more than a factor of 10 higher than the capital cost of your wind turbine, and you won't be surprised if I tell you nobody's doing that. Enter the flow battery. Okay. In a flow battery, you have the energy stored in chemicals outside the cell itself, and you flow them in like a fuel cell and convert high-energy chemicals into low-energy chemicals, doing the electrochemical thing here of ions going through the inside and electrons coming out the outside, and you recirculate. Some of these have reactant and product tanks. Some have just tanks where they can mix the reactants and products, no problem. Now, with storage of chemicals outside your tank, if you need a megawatt, you size your electrodes for 1 megawatt, and if you need more megawatt hours, it's just a matter of big, dumb tanks. And if those are full of big, cheap chemicals, then you win. At least that's the prospect that you can win. And this has gotten attention.
It provides multi-megawatt energy storage solutions using, and I have no idea what this is, vanadium redox fuel cells. That's one of the coolest things I've ever said out loud.
So the president is right. A vanadium redox flow battery is essentially a fuel cell, as I explained to you. But who wants to use the term flow battery when you can use fuel cell instead? The vanadium redox flow battery, or fuel cell, is shown here. It takes advantage of vanadium metal ions in acidic solution that have multiple charge states. And so when it's charged up, you have this state and that state. And when it's just discharged, you have that state and that state. And they happen, you can store them together in that tank and that tank. Right? And so that's the most commercially advanced flow battery that's out there now. But vanadium is a rare and expensive metal. And so the prospect of large tanks full of vanadium is a very large capital cost prospect. Right? And it puts a floor, the price of vanadium puts a floor on the cost of storage at any scale, no matter how good you get at everything else. It's still rather high. So I'd been looking at other ways of storing energy for this problem, and I'd noticed that people in the fuel cell area were making progress using organics in fuel cells. And I started talking to chemists looking for organics that might work in two-way operation of oxidation and reduction. And I learned what a quinone is, and here's a quinone up here. All right, and we'll start down here. This is what's called the hydroquinone. That's just a benzene ring, and there are hydrogens on all the corners, except here there's 2 hydroxys. All right? And this, you can pull off 2 protons and 2 electrons, it'll turn into this quinone right there with the doubly bonded oxygens. And it turns out this came to our attention because they're in photosynthesis. In photosystem 2, this quinone, see the doubly bonded oxygens there, that is going between oxidized and reduced forms over and over again as it accepts electrons from chlorophyll in photosynthesis. So hopefully you ate some quinones for lunch today. Okay. This, though, isn't very soluble. This isn't quite what we need, but there are more complicated quinones with 2 rings, naphtha-quinones, and 3 rings, anthraquinones. Right? And then there are things you can hang off the ends, and that's begins the story of the synthetic organic chemistry quest for a quinone that'll do the job for us. Okay. And so let's look at what quinones do. Here is the oxidized form. Here's the reduced form. This is a single electron addition, a single proton addition, electron addition, proton addition. So all these states are possible, and the rates have to be determined. And sometimes you get rapid reversible 2-electron, 2-proton reduction back and forth. And sometimes you get hysteresis, which is really bad for energy storage, or you can get other things, other pathways through this, or you can get degradation and decomposition. And what we've set out to do was find some quinones that would do the job reversibly for us, where we could take a quinone in this discharge state and a different quinone with different groups on here to change their reduction potential. This would be a hydroquinone, and we'd drive the protons across here and the electrons out and charge it up, turn this hydroquinone into a quinone, and that quinone into a hydroquinone, and then just discharge by reversing those. And as we started looking, the most important thing was getting the reduction potentials right. We can't split water, all right? And we have to have a decent reduction potential difference between the two sides. The solubility is important as well, if you want to get high current densities out. The kinetics have to be fast. The stability of the molecule has to be long-term. They have to cycle many times, thousands of times. And the cost also has to be low, or else we're right back at vanadium. And to show you that, just instead of looking at all these numbers, let's look at just the ones in red, okay? Here's the cell I'm going to show you that we've published performance on at about $27 a kilowatt hour. Vanadium with vanadium, about 3 times that. It turns out this is an overestimate that we published because we've been contacted by manufacturers since then. So these things can be really cheap. They're made of carbon, hydrogen, oxygen, earth-abundant elements, and that's very attractive. And this one, which this one here with a pair of sulfonates on it, has really miraculous performance. This is the one we call, it's our champion, we call it Jesus Christ quinone. Right? And let me show you what it does. We put it, it's here in this solution, all right, and we've got an electrode here, just carbon, and when we make the electrostatic potential of that electrode very negative, we can push electrons down through the electrode and out into the quinone. And as we do that, the electrons are pushing on here, and protons jump on from the acid. It's in pH 0 acid. All right, and then we can turn it around, and we can pull the electrons off as we go to high potential, and there's very little peak separation between these. So this is a very reversible and highly cyclable oxidation and reduction process. If you look at how the reduction potential depends on pH, you can figure out whether you've got no protons, 1 proton, or 2 protons going with your electrons at the same time. And you see for this quinone anyway, anytime you're in acidic conditions, you've got 2 protons and 2 electrons going together. You can put this in what's called a rotating disc electrode. You polish the end of a graphite rod, coat the sides with insulator, and spin it. And it sets up this convective cell where the mass transport is very well understood. And the rate at which you get electric current density out depends on the mass transport, as you can see, as you spin faster, and the overvoltage, the electrochemical overvoltage driving the Faradaic reaction at the electrode. When you go way out to high driving potential, then the overvoltage is getting everything, and all that's left is the mass transport limitation. Out of that, you can get the diffusion coefficient, and so you get that, and now you have only one unknown, which is the electrochemical, what's called the exchange current density, or the chemical rate constant. And so now you have both things conspiring to limit your current density here, but you've already extracted out what the diffusivity is, so then you can figure out what the limiting current density is, what's called IK. So as you extrapolate, this is rotation rate to the -1/2. If you extrapolate these to infinite rotation rate, you can figure out what the kinetically limited current is. And from that, knowing the concentration, you can get the chemical rate constant. And there's the number, all right? That's Faraday's constant. That's the surface area. That's the concentration. And we get a number that's faster than any of these other couples used in flow batteries, and it's 3 times faster than the slower of the 2 vanadium redox reaction rate constants. So this stuff is really fast. These are simple 1-electron outer sphere transitions that you'd expect to be about as fast as you can get. And with the quinones, what we're getting is even faster.
Is it understood why it's so much faster?
No, we don't understand why it's so much faster. We'd love to understand that. And that's, we don't understand that.
Is it possible there's a prefactor missing in the Levitt's description of the mass transport of the electrode?
The question is, have we made a mistake? Yeah, it's possible we've made a mistake.
Is maybe the transport process more complicated than...
Is maybe...
You have, no knowledge of this. I'm told that I don't know what I'm talking about.
Anything's possible. I'm new at this, so, but So it's possible. But these things are really fast. So we put this in a flow cell that looks like this. So we've got this Nafion membrane, standard fuel cell proton conducting membrane. We've got a pair of porous carbon papers, just commercial porous carbon, 10 micron diameter filaments. And we put the hydroquinone up here, all right, and we circulate it around, and we can pull protons out of it and pull electrons out this way. Over here, we took something we just had past experience with because we didn't want to do too many new things at once. This is just bromine going to hydrobromic acid. All right, it picks up these protons, and up come the electrons. All right, and out came. Oh, I'm going to show you some of the guts of this. Some of you know what this is. All about this. You can go to sleep here. But a couple of different flow fields. So a liquid can come in here. These are standard commercial fuel cell flow field plates you can buy. All right, and this just flows by the membrane and then flows out, or you can have a high pressure flow field here, which is dead-ended, and a low pressure flow field over here, and it's got to flow across those ridges, which forces it to go through the porous carbon. And we looked at both of these geometries. We're looking at others. You put porous carbon paper on top with a gasket, Teflon gasket. You put the ionomer on here, the Nafion, and button it up, and you put your fluids through it. Here are the tanks, all right? Not too big at this point. These are big for us. Most of our tanks are much smaller even. So small that we have to use this rather small pumps because we don't want to make a lot of a molecule only to find out that it fails, right? This one works okay. And here's what we got out. So this is the voltage out of our cell. Open circuit around 0.8 or 0.9 volts versus current density. And these units are amps per square centimeter. Okay, this is major league already, kind of first trial out of the cell to reach amps per square centimeter. We're in the ballpark of what the pros do with vanadium and other things. And what we see here is actually very good performance. We started with playing with catalysts because we thought we were going to have to use catalysts. We ended up finding we don't need catalysts really to make this go very rapidly at all. If we take this, there's the open circuit voltage versus state of charge. We've now broken 1 volt. I'll show you that in a minute. And look over here on the right. This is galvanic power. This is the thing that's supposed to be this parabola. It was peaking at 0.6 watts per square centimeter, which again is like the highest literature, peer-reviewed literature value of any flow battery I know is about 1.5, somewhere around there. And so we're already in that league. We've now broken 1. So this is really quite good for a new chemistry. And we have plenty of headroom for further improvement. You wouldn't actually run a cell to store energy near the peak galvanic power density, at least not very often, because the voltage efficiency is too low. These are the same data replotted. Here's now voltage efficiency versus power density. You saw that plot before. And this is telling us that if we wanted, say, one-way voltage efficiency of 90%, the overall cell efficiency is going to be the electrolytic voltage efficiency as you charge it times the galvanic voltage efficiency as you discharge it times the current efficiency, which we'll get to. And altogether, you want that to be 70 or 80%. So 90 is a reasonable target number here. But we're up at about 1/10 of a watt per square centimeter galvanically and maybe 2/10 electrolytically. So this is also very encouraging at this point. These things cycle, and they show no signs of degradation. So here we are imposing a square wave of current density on this cell. And as you impose a square wave, and you just watch the voltage as you drive current in at constant current, when the voltage gets to 1.5, we switch because we don't want to evolve oxygen from the positive electrode. And there's a switch, and now we're putting negative current in, and when it hits 0, we're going to switch again. Okay, so that's all we do, and this goes over and over, hundreds of cycles. With very high, this is capacity retention, which is the number of coulombs you get out in this cycle divided by the number of coulombs you get out in the immediately preceding cycle. And another important thing is the current efficiency, which is the number of coulombs you get out in this cycle divided by the number of coulombs you put in this cycle. And that's a high number too. So these are all very good signs at this point. That was, some of this is new. We had like 10 cycles. That was enough to get it into nature. But commercial applications require many hundreds to thousands. So we got to 700 here. Brian Huskinson, my PhD student, set this up. Cycling this is a long, long process. It was a couple of weeks, right? And he just started it running and went off for job interviews. And when he got back, the water, too much water had left the bromine-bromide electrolyte, crossed through the membrane over to the quinone electrolyte. So he was pumping these big air bubbles through the bromine-bromide. And this goes off here, and the data start going up, to very numbers greater than 1 and less than 0 and stuff like that. So we had to shut that down. We haven't gone back and started over yet because we're doing more interesting things. But anyway, looks like very good performance after 700 cycles anyway. There is a source of current inefficiency, which you can see out of this. So as we change the current density, as we lower the current density, the current inefficiency actually drops. That means as we're giving the system more time to do other things are finding ways to discharge our cell. We've identified 3 potential sources of inefficiency. One is oxygen leaking in through the tubing and reducing that hydroquinone. Now that's reversible. It doesn't destroy the molecule. It just steals the protons away. So that's a current loss. Another is hydrogen gas evolution. A third is bromine crossing through the membrane and going over and reducing the hydroquinone. We know that some of that is going on, and we're in the process of quantifying this so we can understand it and control it better. Overall, then, the energy efficiency, which is that electrolytic times galvanic efficiency times current efficiency versus current density, looks like this. The energy efficiency here, okay, these are targets that we've got for our ARPA-E program. So you see we're doing pretty well. We're not there yet, but we're closing in on it. So this looks very good at this point. So I'm going to become a little bit messianic about quinones here and tell you some of the other advantages before I show you any more data. One we've talked about is that the cost can be very low for the chemicals, and that's a cost per kilowatt hour. Another is with rapid kinetics and very high current densities and power densities, then you can have small area hardware for large power, and that cuts your cost per kilowatt. So there's the potential here for very low cost per kilowatt hour and per kilowatt. And that can matter. These molecules are small, but they're not as small as like iron ions, right? And because of that, separators may not need to be Nafions. They're dianions. Nafion's expensive, as anyone who's bought it knows. So doubly negative charge helps exclude it from a cation conducting membrane. They're bulky. We could put tails on them to make them bulkier, so we have lots of ways of looking at keeping these things from traversing a barrier that are not Nafion. We may be able to get away with cheaper hydrocarbon membranes, and we even have ways that may allow us to use just size exclusion. Okay. We're storing in liquid. We're not compressing gases, which is what we started by doing. And we're not storing in solids, which swell and shrink and swell and shrink with every cycle of your battery, and you have to keep these things from cracking and spalling and buckling over thousands of cycles if you're going to use them. And people working on that know what a very difficult problem that is. Here, our liquids might swell a little bit, but we just don't care. Right? We're storing in water, which makes these heavy. You're not going to drive them around because there's too much weight in water, but they're not going to catch on fire. This is a slide I got from Deborah Rollison of NRL with just some excitement around lithium-ion battery fires, right? When a laptop bursts into flames, that's exciting and funny, but do you want to put a few thousand of those in your garage to store energy for your home? what's that going to do to your insurance rate? These things have taken down airplanes, and they continue to have problems despite all the focused effort on making them better. So organic molecules dissolved in water will not catch on fire. Big advantage if you're going to store a very large amount of energy in one place, and that's what we're talking about. These things are non-toxic, at least some of them, which means unlike some of the other chemistries I'd played with before, this is something I'd put in my basement. This molecule in particular is called Rhine. It's in rhubarb. And we noted this in this paper we published in Nature in January, and some of the press picked up on that. And if you Google rhubarb battery, you'll find press reports about our work. Okay. And the chemistry could be scaled up rapidly. For example, you take anthracene, which comes out of crude oil. It's tar. It's some of the undesired parts of crude oil. It's heavy. They pave roads with this stuff. You just partially oxidize it in air. Air is cheap. And you have anthraquinone, and you mix it with sulfuric acid, oleum, and sulfonates will go onto some of these corners. And a mixed sulfonated anthraquinone gives you the cyclic voltammetry of the red curve here compared to the pure 2,7 Jesus Christ quinone, which is the black curve. And you can see they're about identical. And we'll be looking at seeing how they behave in a cell. Okay. And finally, the combinatorics of organic chemistry, just almost an uncountable number of ways that you can improve these molecules for higher voltage, higher solubility, and so on. Here's just one example, adding hydroxy groups. Right? This is the number of hydroxy groups you'd add to an anthraquinone, and these are theoretical calculations from Alanas Burguzic's group. Our data are the red boxes. Their calculations for those data are the blue squares, and these are other squares. So we should be able to add more hydroxys and bring the reduction potential down, and that will increase the voltage of our cell, and that's important. We're working on that. Here's the cyclic voltammogram for this molecule, which I showed you before. We add 2 hydroxy groups, we can push it down almost 100 millivolts. Add a third hydroxy group, we can push it even further. So we've got almost 200 millivolts gain in open circuit voltage just by what we've been able to do so far in adding hydroxys here. Okay. It also turns out that the composition of the electrolyte matters in ways that quantitatively we can't predict, but qualitatively certainly we can make sense out of using the Nernst equation. And what we see here is open circuit voltage versus state of charge for different molarities of our AQDS molecule, and then different molecules giving us open circuit voltages at high state of charge now crossing 1 volt. So that's sort of an important threshold in terms of getting to respectable voltages for a practical application. Okay. We even have an all-quinone cell, no bromine anymore. I should first say Srinarayan at USC has published a paper on an all-quinone cell in July, but we have one with high voltage, 1.03 volts open circuit. We have a lot of wiggles here because we're making such small amounts of molecules that we have to use these little diaphragm pumps to pump the liquids through. And so what you're seeing here is the heartbeat of our system as it pushes, as it pulses the chemicals through the cell. And so we'll have to do a better job than that before we publish this. But we've got high open circuit voltage, a respectable peak power density already of 50 milliwatts per square centimeter or so. So this is very exciting, and I'm sorry I can't tell you just yet what the molecule is. So we weren't the ones that discovered quinones underwent this rapid reversible two-electron, two-proton reduction. That was actually a discovery of James Conant and his student Lou Fieser. Conant became president of Harvard. Fieser became a famous organic chemist. They discovered this in 1922, and they couldn't explain it because they had to wait for quantum mechanics to be invented. Okay. But they, as you see, showed that there are these reversible reductions that are just so different than the irreversible reduction of ethylene to ethane. And that just doesn't go back and forth easily. This paper was cited only 7 times before we cited it, so it was kind of forgotten, and we found, hey, we can use this now to store energy. And we're interested in why this kind of thing happens. Here's the quinone and the hydroquinone I showed you before. I'm going to put the orbitals on here just to see what's going on. And what you notice is that the redox-active orbital, right, the hydroquinone HOMO, is right there, and it's virtually indistinguishable from the quinone LUMO. You see the protons there on the hydroquinone, and they're missing there, but otherwise, those are almost the same thing. So going from here to here, you're not reconstructing the orbitals. You're popping protons off, and electrons just come and go. There's also, if you look sort of in the plane, at the OH bond right there, that proton that's going to come off, oh, there it is, there's almost no electron density. There is no, it's a nodal plane for the active orbital. And that may be important too. We don't know at this point which of these is essential or if both. And we're looking at other molecules now to see if we can understand that as well. Contrast that with ethane to ethylene. So here's the HOMO of ethane, all right, and the LUMO of ethylene looks completely different. So there you have this major reconstruction of the bonding. So I will wrap up and say there are redox-active organics. There's a lot of them in biology, it turns out. I had no idea, right? And we've harnessed one, and there are lots of others. Energy storage looks very promising in this case. Other applications may be there. Hydrogen storage, stationary hydrogen storage, for example. We're thinking about others. This redox flow battery is a high-performance cell right off the blocks. Proves the concept, but there's plenty of room for improvement in terms of improving the molecules, the separators, and the engineering of the electrodes and the fluidics, for example. At the end of the day, whether this will change the way electricity works on the grid depends on how low the cost will be. And I think we've brought the cost of the chemicals way down so that the cost of the rest of the system is going to be really important. And we don't have a lot of control over that, and it will really take a lot longer to figure out how low the cost of the balance of system will be. But that's going to be the important arbiter at the end of all this. So I'll end with a couple of fun facts about quinones. You can go to the drugstore and get this one to bleach dark spots off your skin. Okay. This one's in aloe vera, so it actually has soothing properties there. Okay. Vitamin K is also a quinone. You see the pair of doubly bonded oxygens there as well. It's found in green plants as well, and hopefully you ate some of those for lunch. These quinones can be very popular. How popular are quinones? Well, 9 out of 10 male cockroaches find them completely irresistible. So we're thinking if we can make a battery out of this one that for energy storage in the kitchen, that could be a really big hit, don't you think? So I'll end by acknowledging my sources of support and collaborators, and then I'd be happy to take questions. This work was seeded. The first seed we got was from the Harvard University Center for the Environment. That was just like half a student year to let me start thinking about flow cell storage. And that was important, but we didn't have the right chemistry. And then the School of Engineering and Applied Sciences gave me a seed only if I would collaborate with someone outside the school. So I had to talk to chemists. And that was what led, that was critical, actually talking to chemists. And I talked to Roy Gordon, here he is, leading our synthetic chemistry effort, and Alana Sputaguzic, leading the theoretical chemistry effort. We had some other internal funding. We hit big with an ARPA-E award about almost 2 years ago now, and that's supporting us at this point for technology development. And I also have to point out, we've got, here is Brian Huskinson, who built the first working quinone cell, and Mike Marshak, who made the chemistry work. Mike is on the faculty search circuit now. He's a terrific young chemist. He's a PhD student at Dan Nocera. You should be lining up to make him offers. He's made the chemistry in this program just fly. He's made his own cells as well. And we're collaborating with a small company. Their job, Trent Moulter and Sustainable Innovations, their job is to make something that isn't put together with alligator clips and duct tape and actually looks and works well and could be sold and used in people's basements. So thank you. I'd be happy to take questions.
Great. Well, thank you, Mike, for the very wonderful talk. And we'll take some questions. Just if you have a question, just...
Yes, that's good. That's a good idea.
Batteries.
On the nature work. It looks like, when I look at the numbers, you have an energy density of about 5 kilowatt hours per cubic meter. So the energy density is about 2,000 times smaller than that in gasoline.
Our actual energy density is higher than that. It is 50 watt-hours per liter, which I think is an order of magnitude higher if I just did the conversion in my head. But it's 50 watt-hours per liter per side. So 1 liter of pozolite and 1 liter of nailite give you 50 watt-hours. Right? So with the system, though, it's 25 watt-hours.
So is it, you had 0.1 molar solutions, that's what I calculated.
Our battery is with 1 molar solution.
Oh, with 1 molar?
Yeah.
So you had data with 0.1 molar here.
You have data with lots of different concentrations, but our battery is running with 1 molar.
1 molar. So then it's 50.
So that's 2 molar electrons, right? 1 molar molecules is 2 molar electrons. We have some solubilities up to 3 molar, but we're not really pressing hard for high solubility because it turns out one safety feature, if there's a burst of something and 2 electrolytes mix, they're going to discharge and they're going to generate heat. And if your concentration is low enough that cheap plastic tubing will succeed in containing that, then you can win. So energy density isn't always a good thing.
And I had just a very quick question. These are all basically relatively reactive systems. Do you get polymerization in the electrical process?
Do we get polymerization? We haven't seen it, and we're stunned, and we don't understand why we don't get polymerization. We thought we were going to have to study polymerization and theoretically look at polymerization pathways and figure out how we're going to protect against that. We haven't had to yet. Now, we've only made a couple of molecules, different molecules work in a cell. And as we look at more, we may run into this kind of behavior. What are the limits in reduction potential as you functionalize? So on the low end, I showed you we can get, theoretically, south of standard hydrogen electrode, right? By a couple hundred millivolts. Alan and his group, they've calculated now the reduction potentials of some 10,000 molecules. So we have these libraries, and they've calibrated them against a few experimental points, so we have a reasonable way of estimating them. And I forget in my mind, there might be a 2.5 volt spread, but that doesn't mean that they're easy to synthesize or, at the end of the day, inexpensive. So there has to be some optimum between potential and synthesizability, and stability is important, and solubility.
What methodology other than just looking at the redox potential be used for identifying which atoms you use such a huge range?
What methodology do we use to screen quinones? So we discovered after half a year of wandering around in the woods that sulfonation was really good for solubility. And so now we're looking at other ways of doing that, but basically we have sulfonation and we may be able to improve it, but now we think, okay, start with sulfonation, Putting hydroxys on there also gives you some solubility. That pushes the potential down. Sulfonates push the potential up. We've looked at a lot of the common small atomic groups, adding them to all the various places that you could add them in a benzoquinone, naphthaquinone, or anthraquinone. We've started to look at chains like this. So the theoreticians can go much more rapidly, systematically. And we've gone, basically what we've been able to do experimentally, a lot of it we've gotten there before the theoreticians, and it's because of Mike Marshak's insight, not mine. Right? But the theoreticians are catching up, and we expect they'll be able to go ahead and tell us some less obvious things now that they're calibrated.
Can you comment on the effective temperature of the electrolytes, whether it is better or worse? I would imagine with very large tanks, you can vary them to ensure that 50 degree Fahrenheit
The question was, which I'll repeat for the recording, about the effect of temperature on operation here, is because I suppose it's motivated by the vanadium redox battery people. Their batteries are very sensitive to temperature. We haven't found that sensitivity. Higher temperature seems to give us higher performance, but we haven't tried to make the temperature go up. We haven't put any temperature controls in our systems yet. We have small cells. The pumps actually put enough heat into this system. Between the pumps and the inefficiency, the electrical inefficiency, we get some heating to 30 or 40 degrees C, and then it just reaches a steady state and we do our experiments. At higher temperature, the resistivity, the ion conductivities go up of the Nafion membrane and the electrolyte, so those things help a bit, and eventually we'll probably put in some temperature control and start to look for optima. But right now we don't see we don't see high sensitivity to temperature, either high or low.
Yeah, I came a little late, so I don't feel like you've already answered this. What do you view as the challenges to going toward a very high cycle number with batteries?
The challenges of going towards a very high cycle number. We expected to find molecular degradation pathways, and we expected to have to pull out all the stops to figure out what those pathways were and find the vulnerable points on the molecules and figure out what to put there in order to protect the molecule. It hasn't happened yet. It may yet, right? We've only done this 700 cycle experiment once, and there may be some small loss that we're just not seeing yet, and it'll be important because you want to run these things at many thousands of cycles. So it could come up. There could be degradation. There could be polymerization. As we change to molecules with lower reduction potential and others with high reduction potential, all the things that maybe we're lucky with Jesus Christ quinone, maybe our luck will run out and we'll have to deal with all these things.
Maybe two last questions.
Just actually a point of information, but all of the hydrogen peroxide made in the world uses the quinone couple. In that case, it's being done in an organic solvent, and the anthraquinone turns over thousands or hundreds of thousands of times. To my knowledge, the only thing that happens, well, to keep it inorganic, they have an alkyl tail on the 3 position. So where you have your sulfur, they have an alkyl tail there, and everybody has a little bit.
Here?
No, in the, where you have your sulfur.
So here?
Yeah, there. I guess it's the same, actually. The only thing that happens in that case is slowly the alkyl tail oxidizes to the organic acid, and then the quinone becomes insoluble to the organic solvent. And it will slowly drop out, or be actually extracted into the water.
But the quinone itself, the framework, the anthracene framework goes around forever. I love it. I love it.
So you focused all on the quinone side of the cell, but a large part of the voltage actually comes from the bromine part of the cell.
I'm surprised that you managed to run these things so long with an Nafion membrane and bromine, because I've seen many, many membranes chewed up by bromine oxidizing ionomer membranes. Have you just gotten lucky here, or did you do something special?
Good question. So bromine chews up Nafion. Bromine is aggressive stuff, that's for sure. And I don't think we've chewed our way through any membranes with bromine. The bromine is always in there with hydrobromic acid, so it's forming tribromide. I don't know if that makes a difference or not in terms of the aggression on the membrane. But
You think you're going to the tribromide ion, and you're going back and forth between Br minus and Br3 minus?
Usually that's what we're doing. Sometimes we put more bromine in. We haven't destroyed membranes that way. We've destroyed plates, graphite plates we've actually cracked from bromine going in and intercalating, but that's another story. But let me just say, here we're getting rid of bromine, and I'm very happy to get rid of bromine, all right? But the small company we're working with, Sustainable Innovations, they are really good at handling bromine, and they work with ICL, the world's largest producer of bromine, who have ways of complexing the bromine, and that's all their department. We're not dealing with complexing, but I think bromine has legs if it's done in the right way, and that's not what we're focusing on. Right? We're focusing on high potential quinones and low potential quinones.
All right, well, we'll have a little brief meeting outside after this.